Hello, Mr. Claudia here, and today we are going to continue learning about optimization, which, as you know, is finding the max or min point for usually a real-world problem. Before we get to our lesson on the algorithm for optimization problem solving, we need to talk about extreme values. Now, this word extreme might make you think, oh, this is going to be a really intense lesson, but that's not really what extreme means. The word has kind of changed its meaning a bit in the English language. But the extreme means the furthest point, or you could even say a behavior that's at the edge. When we talk about, say, extreme sports or extreme skiing, we're not talking about super intense sports. We're talking about sports that are at the edge of what people can do. Another example of the word extreme I like to talk about is the extreme points of the Earth, which you may or may not be familiar with. I mean, here's the extreme point. It's at the edge. It's the highest point, highest elevation. You probably know this. This is Mount Everest, right? That's one of the extreme points of the Earth. But there's also this point. Now, if this is the highest elevation is one extreme value, then the lowest elevation would be another extreme point on the Earth. And this, you probably know it as well, hopefully. That's the Dead Sea, located in the Middle East. I think it's like a few hundred meters below sea level. It's a very salty lake. It would be a cool place to go, and it would be an extreme point. There's another extreme point there's a few of them on Earth, and it's called, you can see it depicted here for North America. This is the pole of inaccessibility. And that is the furthest point from an ocean. So there you go. If you want a new challenge, you can try to collect all the extreme points of the Earth, the highest point, the lowest point, but also the point that's furthest from an ocean. And it's somewhere, I guess, in Nebraska, or where would that be? Dakota or something like that. There's also one in Asia, the furthest you can get from an ocean. These are all extreme points, and it kind of gets us ready for our lesson on the extreme value. So previously, we've been able to find the max and min points of a function, which is great. But usually in optimization problems or real-world problems, we're looking at a fixed interval. So when we talk about finding the absolute highest point, not only do we want to find the max and min points, those peaks and valleys, but we also want to see maybe the endpoints happen to be the highest or lowest point of the function. So let's say I was asking you, can you tell me what's the highest point of these functions below? Well, if I look at this function, this graph, and again, it's over a short interval, well, it's pretty clear to me that this is the max here, right? And it's pretty clear to me here that this is the min. Okay, let's go to the second graph. What's the highest point of the graph? Well, again, this is the highest point. And what's the lowest point? Well, this is the low point. But it's not the absolute lowest point of the whole graph, right? If I asked you to find the smallest value, it's actually over here. It's this end point. Now, previously this wasn't a concern because the functions went on forever. But now, because we're in a real-world problem, there's some sort of end point. There's some sort of bounds. So my minimum is right here. So the question is, how do I discern this from this? Like, what do I call this? What do I call that? So when we talk about the extreme points, or we're talking about the most max or the most min point, we use the term absolute max. And similarly here, these are absolute max and absolute min. So the absolute max and absolute min can be the same as the relative max or the relative min. Or they can be the endpoints. So this one here would just be a relative min. Or local min, we called it. This last graph, well, let's see. Okay, the maximum point is right here, the absolute max. And the absolute min is over here. It's the lowest point. These are also called global max and global mins. And just like we talked about before, the relative min or local min is here, and the relative max or local max is here. So, and then I've just listed the definitions. So what we just learned today, the absolute max or global max, so absolute max min, global max min, these are the largest, smallest values on the entire interval. And then the relative max min or the local max min, these are the peaks and valleys. We found these in the curve sketching chapter. Hopefully you remember where these occur. Remember, they always occur at points where there's a horizontal tangent line. So that means that the derivative is equal to 0. So relative max min points can only occur where the tangent line is horizontal. That is where the derivative is equal to 0. So to find these points, we have to set the derivative equal to 0. To find that, but then we have to check these points to make sure. Note that the function can have many relative extrema, but it can only have one absolute extrema on a given interval. So this makes sense, right? Like I can have a graph with a lot of relative maxes. It could have all these little humps, but it can only have one absolute max. And similarly for the minimum. So let's talk about how we find this and the procedure we're going to go through. If I wanted to find the absolute max min, and I remember this only works if I have an interval, function on the interval, I would find the first derivative, then all the critical points where the derivative is equal to 0. Then, so that would give me all these points. Then I'm going to verify my solution by eliminating any extraneous values. It could be that one of your points you found is outside of the interval, so then you don't have to worry about it. And then you're going to compare your solution to all the interval endpoints. So once I know that there's a max or min or critical point here and a critical point here, I'm going to find the y value, but also find the y value at the interval endpoints. And I'm going to compare those y values, and then the highest one is going to be the absolute max, and the lowest one is going to be the absolute min. Let's do a problem and see how this works. Turn it up page. Okay, find the absolute maximum and minimum of this function on this interval. Okay, so this is not quite a word problem, but it's asking for an absolute max, right? Which means I have to do this kind of procedure. Remember, the other term for this is global max, global min. So we need to find the derivatives first, right? That's what my procedure was. And just like a normal question, I'm trying to find the max min points. So there's my derivative. Now, for critical points, we set the derivative equal to 0. So I have 0 is equal to 3x squared minus 12x. The easiest way to solve a quadratic is to factor. So I'm going to factor it to 3x. I'm left with x minus 4. So then I have x is equal to 0, and I have x is equal to 4. So now those are possible max min points, right? Those are probably relative maxes and mins. But when we're dealing with absolute max min, it's not enough to just look at these 2 points. You also have to look at the endpoints, -3 and 5. So we're going to test the y values of the critical points and the interval endpoints. Okay, let's do it. So we have, let's start with f at 0, which is going to be 0 cubed minus 6, 0 squared plus 5, which is just 5. Then I have f at 4, which is 4 cubed minus 6, 4 squared plus 5. We usually have calculators in our optimization chapter, so let's just go for it. Minus 27. I need to look at the endpoints now, so I have to look at f at negative 3. So that's negative 3 to the power of 3 minus 6 times 9. Negative 76. And then I have f at 5, which is 5 cubed minus 6, 5 squared plus 5. So I have 5 to the power of 3 minus 6 times 25 plus 5. And that gives me minus 20. Okay, so now I have a better idea of what's going on. I've tested my relative maximum points, I found them out, and then I tested the endpoints. So therefore, the absolute max is, what's the absolute highest number here? Oh, it occurs at 0, 5. And the absolute min is, what's the smallest value? Negative 76. So that was one of the endpoints. Negative 3, negative 76. So let's see, we do have to check the endpoints. What I could show you is, I know like you probably are kind of imagining this yourself, but like just if I were to do a little sketch of what I found. So we have 0, 5, something like that. We have 4, negative 27, so something down here. Not gonna go that far. 4, negative 27. We have 5, negative 20. And then we had negative 3, negative 76, so something down here. Not to scale really, but so we have kind of this shape. We know this is a max, min. Right, so that's negative 3. That's 4. That's 5. So you get a little idea of what was happening here. So these are relative max and mins, but of course we were looking for the absolute, so we have to consider this endpoint. That's it. It's kind of a neat little strategy. It's something we should be aware of when we have word problems. Here I'll start. We're going to be looking at a lot of word problems in our next lesson, but we have one more for you to get excited about. The amount of light intensity on a point is given by this function, where t is the time in seconds. Okay, so as time goes on, the amount of light changes. And time can only be between 0 and 14. Determine the time of minimal intensity. So when we read this question, we're being asked to find the minimal intensity. So I want to find the min point of this function, which would mean I have to find the derivative and set equal to 0, blah, blah, blah. But because there's an interval, I also have to check the endpoints. So let's find the derivative. And you betcha, you have to use the quotient rule, or least favorite thing. So the derivative of the top thing is 2t plus 2 times the derivative of the bottom thing, which is t plus 2, minus the top thing, which is t squared plus 2t plus 16 times the bottom, derivative of the bottom thing, which is just 1, all over the derivative of the denominator squared, so t plus 2 squared. Okay, and now I'm going to clean this up a little bit. I'm going to expand so I can collect my like terms. So I end up with 2t squared plus 4t plus 2t plus 4 minus t squared minus 2t minus 16 all over t plus 2 squared. Okay, now let me clean this up a little bit. So I have 2t squared minus t squared, so I get t squared, 46t minus, I just have 4t, and 4 minus 16 is minus 12. And that's over t plus 2 squared. Okay, what am I trying to do again? Oh yeah, I want to find the min points. So for the critical points, we set the derivative equal to 0. Okay, and now I need to solve for this function with equals 0. Well, if I cross multiply, I end up getting rid of that denominator. Now I just need to factor. That's how we solve a quadratic like this. I have 6 and 2, positive 6 minus 2, I believe. So now I have two answers. I have t equals negative 6, and I have t equals 2. Well, right away, I've got a bad feeling about this because, t is time. Usually can't have negative time, and indeed you can't, right? The interval for t is between 0 and 14. So right off the bat, I can save myself some trouble. This is outside of the interval. So see how in a word problem, unlike curve sketching, we do have to kind of use our brains a bit, and we have to remember the problem we're trying to solve. Now, this is great. I know that this is probably a minimum point, but it's not enough to just look at this point because there's an interval. I have to look at the endpoints as well. So let's start by finding I at 2. So I'm going to check critical points and endpoints. So I have I at 2, which is equal to 2 squared plus 2 times 2 plus 16 over 2 plus 2. Can I figure that one out? That's 4 plus 4 plus 16 over 4. So that's 24 over 4, which is 6. Okay, so that's the 1 point. But then I also have to check I at 0, right? That was the first endpoint. So I get 0 squared plus 2 times 0 plus 16 over 0 plus 2, so that becomes 16 over 2, which is just 8. And then I have I at 14. Oh, I'm going to have to get a calculator for this one. 14 squared plus 2 times 14 plus 16 over 14 plus 2. Let's solve that. 14 squared plus 2 times 14, oops, plus 16. That's 240 over 16, which is 15. So the question was asking me what was the point of minimum intensity, the time of minimum intensity. So therefore, the minimum intensity occurs at t equals 2 seconds. So you can see that even though it was not the endpoints, it's still an important process to check because you never know, it could happen. Now, traditionally in IB, I find that these questions are they're short questions. So usually it's it is actually the point, the relative max min tends to be the absolute max min, but it's not guaranteed. And so this is a skill we have to be aware of. Okay, and that's that. So your homework for tonight is page 244, number 1 to 5. Okay, good luck with that, and we'll see you next time.